All right, so let's see briefly what is inside the router. We will talk about input ports, switching, output ports, buffer management, and scheduling. So let's look at the picture. This is high-level view of generic router architecture. There are input ports and there are output ports. So in the middle, you have high-speed switching fabric, which actually determines which input ports data will be sent to which output port. So that is the main idea. So this is the routing processor. So again, the upper part is routing management control plane. You do it at the software level, operates in millisecond time frame. Here, forwarding data plane operates in nanosecond time frame. This is why when you jump between many routers, your data actually reaches to the other side in generally in milliseconds. So this is why generally we prefer this part to be done in hardware. Okay. So there are some physical parts. I will briefly read the slides and move on. So at the physical layer, you have the bit level reception here. You transport it to link layer, like protocols like Ethernet and so on, which is the topic of the next layer. Once you receive it, you actually put it inside the your queue. This is lookup, forwarding, and queuing. Decentralized switching using header field values, lookup output port using forwarding table in input port memory, match plus action. Goal, complete input port processing at line speed, because if you do it slower than the line speed, then you will observe slowdowns, right? Input port queuing, if datagrams arrive faster than forwarding rate into switch fabric, it will fill the buffer. So this is what I meant by buffer overflow. Then you have to, drop some of the packets because you cannot store everything. You might think that, okay, maybe we can increase the memory and store everything. I mean, not everything, but more, right? But again, if you keep a lot of data in the buffer for a long time, this would also cause slowdowns, right? So there have to be a nice spot for the time to wait in the queue and, the size of the queue and so on. So destination-based forwarding, forward based only on destination IP address. This is the traditional method. Generalized forwarding, forward based on any set of header field values. Okay. So destination-based forwarding works as follows. These are the destination address range. So these are actually IP numbers written in as bits, right? Because we haven't seen the IP datagram yet, which is the next topic. But just think that in the IP version 4, we have 32-bit IP addresses. When you convert them into bits, this is what you see. So you prefer in this example, there are 4 output ports. So we call them interfaces. So by looking at the destination address, you will choose which port you are going to send. So you observe that almost all of them, let me check. All of them start with this part. So this prefix are identical here, right? But the remaining part changes. So you send from here to port 0, this one to this to 1, and so on. So the question is, what happens if ranges don't divide up so nicely? So this is actually an important thing. So maybe, here the point is that maybe at some port you have 5 computers, in the other one maybe 2,000 computers. So you have to divide these ranges so that they can support that many hosts. So idea is like this. So in this example, let's see. Yes, only the last part changes, right? So the good thing is that when you keep this data in tables, you actually need to store the first part, right? So this way, the size of instead of writing every IP destination IP address and write a port, you are actually determining a range, which actually makes it smaller for the forwarding table. The size so becomes smaller. This is the idea. So this is what I'm trying to say was the longest prefix match. When looking for forwarding table entry for giving destination address, use longest address prefix that matches destination address. So here we should have some examples. As you can see, these two start with the same thing, right? By star we say can be anything. So, but here we have more fixed bits. So 3 bits are also fixed. So this means that if a data matches this one, the longest one, it will go to this link layer. But if it doesn't match with this longest prefix, but matches with only this part, then it will be sent to this port. Okay. So here are some examples. Let's see. Yeah, this one matches this one. As you can see, the next bit starts with 1. So it doesn't match with anything. But here, as you can see, this one starts with 3 zeros. So it matches this one in a better way. So it should send it to here because this is the longest matching. Okay. This is important because at some point, you might give IP. Internet service provider might give this IP address to you, but people were using this block by other servers. So this way, with the longest prefix matching, they will know where you are. This actually allows you to have communication. So the question is here, it says we will see why longest prefix matching is used shortly when we study addressing, but I already gave you the answer. Longest prefix matching often performed using ternary content addressable memories, TCAMs. Content addressable present address to TCAM retrieve address in one clock cycle regardless of table size. So here's an example for a Cisco device. It can, it can store 1 million routing table entries in TCAM. So you can store a lot of data. So now let's look at switching fabrics. There are 3 popular methods. Transfer packet from input link to appropriate output link. Switching rate at which packets can be transferred from input to outputs, often measured as multiples of input-output line rate. N inputs, switching rate, n times line rate desirable. This way you don't cause a slowdown, right? Because if there are n ports, you should switch in a very fast way so that it should be at least, n times the rate of the line, which is r. So ideally, it will be at least n times r. This is why we want to do it in nanoseconds. Okay, so 3 major types of switching: memory, bus, and interconnection network. So let's briefly see how it is defined here. Switching via memory. This is the first generation routers. Traditional computers with switching under direct control of CPU, packet copied to system's memory, speed limited by memory bandwidth. So you actually send the data to memory, find it, and depending on the output, you send the output. So this is limited by your memory bandwidth, right? If you're going to ask a lot of questions to the memory, you can cause a slowdown. Switching via bus, datagram from input port memory to output port memory via shared bus. Here the keyword is shared bus. Since you are sharing it and it is a single bus, if there are 2 data at the same time, one has to wait in the queue. That is the main catch here. Bus contention, switching speed limited by bus bandwidth. For instance, in the Cisco device, we can have 32 gigabits per second for each bus, sufficient speed for access routers. So here the idea actually is like this. For instance, if you have 3 input ports and 3 output ports, since they are directly connected, if all of these ports send data to the different output port, then you don't have any waiting, right? But if these 2 inputs send to the same output, then you have to wait. So this is the main catch here. So switching via interconnection network. Crossbar closed networks, other interconnection nets initially developed to connect processors in multiprocessor. Multi-stage switch, n times n switch from multiple stages of smaller switches. So here the thing is that you are actually connecting every bus with itself. But if this data from this port is going to this one, you are actually, turning on these parts so that you actually direct data from here to here. So this is what we mean by switches. Exploiting parallelism, fragment datagram into fixed length cells on entry, switch cells through the fabric, reassemble datagram at exit. Okay. Scaling, using multiple switching planes in parallel, speed up, scale up via parallelism. For instance, here's an example of a Cisco device router. Basic unit, 8 switching planes, each plane 3-stage interconnection networks, up to 100 terabits per second switching capacity. So as you can see, these devices allows huge data transfer. Input port queuing, this is what I was trying to explain. If switch fabric is lower than input ports combined, queuing may occur at input queues. Queuing delay and loss due to input buffer overflow. So that is what I meant. So here you have 3 input ports and 3 output ports. Here the red data actually going to this red output port. So if you send both of them at the same time, one has to wait. This is the idea. So only one red datagram can be transferred. Lower red packet is blocked, right? So at time 1, this red packet is sent and this blue packet is sent. But this one waits. So in the next one, the top blue goes to blue port and red one goes to this one. So at this part, there is no queuing, but observe that the green packet is waiting here still. Actually, if there weren't any queue here, at this time, green will be sent to here. Okay, this is, we talk about hole blocking. Head of line blocking. Queue datagram at front of queue prevents others in queue from moving forward. So if your queue is, becomes really huge, you cannot have infinite memory. You have to drop some data. This is what we meant by buffer overflow. Buffering required when datagrams arrive from fabric faster than link transmission rate. Drop policy, which datagrams to drop if no free buffer. So question asks if, one might think that if it is full, you drop the new ones, but actually you might have a different idea and, drop some others waiting in the queue and, accept the new ones. Actually, since we have many headers, we can decide what to keep and what to drop. This is what it is meant here. So datagrams can be lost due to congestion, lack of buffers. Scheduling discipline chooses among queue datagrams for transmission. So priority scheduling, who gets best performance? Again, this leads to our topic network neutrality that we mentioned in a minute. So this is actually an important slide. Yes, there are many things to be considered here. The network neutrality is one of them, but we are moving on. So output port queuing, buffering when arrival rate via switch exits output line speed, queuing delay and loss due to output port buffer overflow. So there's a rule of thumb from RFC. Average buffering equal to typical RTT, say 250 milliseconds times link capacity C. So this is the amount of buffer you should have. So in this example, if C equals to 10 gigabits per second, you should have 2.5 gigabit buffer. But in newer documents, the recommendation is as follows: RTT times C divided by square root of N. Recall that N are the number of ports that we mentioned. Yes, but the bad thing here is that too much buffering can increase delays, particularly in home routers. So long RTTs, poor performance for real-time apps, sluggish TCP response. Recall delay-based congestion control, keep bottleneck link just full enough, busy but now fuller. That is the main idea. So buffer management, there are some ideas here. Drop, which packet to add drop when buffers are full. Tail drop, drop arriving packet. Priority, drop remove on priority basis. So this is, at this point, you have to decide what is priority, which one is more important. So there are a few slides here that we are going to talk about. Packet scheduling, deciding which packet to send next on link. First come, first served, priority, round robin, weighted fair queuing. So actually these ideas appear almost everywhere in computer science, right? So this is also what happens when you have a CPU. So the operating system has to decide which work will be done by the CPU. If you use first come, first served, and for instance, if you have one CPU with one core, and let's say that you are trying to print out something, but there's a problem, so you're waiting that process, so you cannot do anything else. This is why in the past, our computers froze a lot. You are listening to a music, but you try to surf on the internet, and then it crashes. These are the things you have to take care at the design level. So when an operating system is designed, they first decide what will be the scheduling algorithm. So same thing applies here. You can here use first in, first out, FIFO, or first come, first served. So this is what happens when you go to coffee place and order coffee, right? Prior to scheduling, arriving traffic classified, queued by class, any header fields can be used for classification. So think about this again in a bank. So you can think that also in banks, we have first in, first out, first come, first served. But actually, generally what happens now is that when you take your number, you actually press a button which describes why you are there, right? So actually you classify the customers there. So there are 2 different queues, or sometimes 5 different queues for 5 different kind of operations. So this is what actually mean by priority. So send packet from a highest priority queue that has buffered packets, then of course you send them in the order of first come, first served. So in this example, there are some things that is showing, at which time which packet is served. Round-robin scheduling, arriving traffic classified, queued by class. Any header fields can be used for classification. So in this case, you have 3 classes. So there are 3 queues. Server cyclically, repeatedly scans class queues, sending 1 complete packet from each class if available in turn. So there's the weighted version of this. This is generalized round-robin. So it actually guarantees minimum bandwidth, because in the previous one you might wait in the queue for some time if your class has long queues, but this kind of solves that problem by taking weighted average actually. So it provides some kind of minimum bandwidth guarantee. Yeah, let's finish this with network neutrality. So what is network neutrality? Technically, this is how an ISP should share, allocate its resources. Packet scheduling, buffer management are the mechanisms. Social economic principles, protecting free speech, encouraging innovation, competition. Enforce legal rules and policies. So different countries have different takes on network neutrality. Again, with the war in Ukraine, this is, ISPs can limit, Russian traffic and so on. So this was a hot topic around 2015 and later on. So there was an FCC order which actually described 3 rules. This was the order on protecting and promoting an open internet. So no blocking, shall not block lawful content, application services, or non-harmful devices subject to reasonable network management. No throttling, shall not impair or degrade lawful internet traffic on the basis of internet content, application or service, or use of a non-harmful device, subject to reasonable network management. No paid prioritization, shall not engage in paid prioritization. So this was a huge topic because in United States, it was discussed for a long time, because some companies, there are huge companies like Facebook or Google, which actually provides a lot of people are using these services. So actually it might be meaningful to, prioritize them. So there was a discussion, maybe, they should pay more money and, get the more bandwidth and so on. But this would mean that, services that are provided by not that rich companies will have some slowdown. So this is the hot topic for the last few years. So is an ISP a telecommunication service or an information service provider? The answer really matters from a regulatory standpoint. So the U.S. Telecommunication Act, so Title II imposes common carrier duties on telecommunication services, reasonable rates, non-discrimination, and requires regulation. For the information services, no common carrier duties, not regulated, but grants FCC authority as may be necessary in the execution of its functions. So legally, there are some gray areas, which is also used in the war in Ukraine.